thanks everyone for joining. So this is going to be our last seminar on prediction modeling and machine learning before the summer. And we are very, very happy of having with us Mihai Ermaliuc. I hope I pronounced this correctly, Mihai. Sorry if not. So Mihai belongs to the Data Science and Subcomputing Lab in the Department of Computing at the Goldsmiths University of London. He's working with Daniel estimates, and there Mihai is developing his PhD in a part-time basis, whilst he's also working on industry. You know, that is very challenging, but it's very beneficial at the same time. So his research is focused on neural networks and deep learning. He's particularly developing generative adversarial networks that are called GANs algorithms, and he's planning to apply this to dementia prediction as a next step in his PhD. Let me tell you a little note that the work that Mihai is presenting today has been already published by Springer, and that recently got the Best PhD Student Paper Award in the International Conference of Engineering Applications of Neural Networks. So Mihai, lots of congratulations for this achievement. And I am sharing the preprint of this work in the chat so that if you want to have a look to the work that he has written and that he will be presenting today, you have a chance. So that's all from me, Mihai, just telling the audience that if you want to make questions after the talk, you will be able to do so. You can open your mic and just ask or write the question in the chat, and I can read the question for you. So thanks very much, Mihai. Thanks everyone for the attendance, and let's start when you are ready. Thank you.
Thank you. I will share my screen momentarily. All right. Can I please check that you see the screen?
Yep.
Yes. Yes. Yes.
Right. So first of all, thank you for inviting me here, and welcome to the presentation of our paper, Creating Ensembles of Generative Adversarial Network Discriminators for One-Class Classification. This should take about 20 to 25 minutes, and we will be looking into how we can use the training process of a generative adversarial network, or GAN, to create a one-class classification model. Specifically, we will see how by slightly altering the training process of a GAN, by collecting the discriminators it produces at every stage, and finally by ensembling them together into a single model, we obtain a one-class classification model with pretty good results. Again, as you will see, it surpasses many other deep learning-based models when tested on highly dimensional and sparse data sets. This piece of work is part of my ongoing PhD, and also part of the research within the Data Science and Soft Computing Lab, led by Dr. Daniel Stamate at Goldsmiths University of London, with significant contributions from Professor George Magoulas from Birkbeck University of London, and from Dr. Aida Pu, again from Goldsmiths. And it aligns with the research directions of the lab, which include practical applications of generative adversarial networks, prediction modeling approaches in healthcare, using machine learning and natural language processing for sentiment analysis, stock market prediction and fraud detection, or AI prediction of colors, and so on. Let us turn now to the topic of the paper. So arguably the most common and well-known case for classification in machine learning is binary classification. In this case, we have a data set containing two classes, and we need to train a model to separate them. There is also the case when our data set contains more than 2 classes, and this is the multi-class classification problem. It's not so far removed from binary classification and actually can be reduced to a number of such problems. But there is also a third case, when our data set contains instances from a single class only. And in this case, we usually want to learn to separate that single class from everything else. This is the one class classification problem. As one might imagine, it stands out as much more challenging than its binary or multi-class counterparts, but also much more versatile and rewarding if we can actually do it. It has applications on topics such as novelty detection, anomaly detection, fraud detection, classification with imbalanced data, or even binary or multi-class classification can be achieved with single class classification. As an overview of the methods, we can use a taxonomy defined by Alexei Mazielis and categorize them, categorize one class classification methods in 3 categories. Density models that attempt to estimate the probability density function of the data, or boundary models that attempt to directly place a border around the data, or reconstruction models that project data onto a lower dimensional space and back, then measure the reconstruction error. In terms of performance, older methods such as support vector data descriptors or maybe isolation forests tend to perform well on low dimensional data, albeit with a bit of tweaking. However, they usually break or become intractable in higher dimensions. But with the advent of deep learning techniques during the past 10 years, there's been a fair amount of research on adapting deep learning for one class classification. And the resulting methods deal much better with highly dimensional data sets. And actually, our work is inspired by one such method presented by Pereira et al. In 2019, detailing a one-class classification model as a combination of autoencoders and generative adversarial networks, and at that time, state of the art. Since we mentioned the generative adversarial networks, they are a major building block for our algorithm. So let us focus on them for a while. They are essentially generative models, but stand out by being capable of creating highly realistically looking data. Just take a look at the picture on the right and notice how well detailed and realistic it looks. But well, it's a fake. And if you go to thispersondoesnotexist.com, you would be able to generate such images yourself. So this is an example of what GAN can do. So let us discuss a bit what they look like and how they train. And in the following slides, we will also see why they are important to us. A GAN takes in an unlabeled or single class data set and is composed mainly of 2 models. The generator, the generative model, which starts out by outputting random noise, but after the training process is complete, it will be able to create samples that look as if they are coming from the real data set. but without imitating, without copying exactly any sample from the dataset. The discriminator is essentially a classifier whose role is to place itself to distinguish between samples coming from the real data and samples coming from the generator. During training, these two models play a game with each other, hence the name adversarial, where the discriminator, as I was saying, learns to distinguish between samples coming from the generator and samples coming from the real data, while the generator learns to tweak its output, its generated samples, so that they fool the discriminator into classifying them as real. This game goes on ideally up to a point where none of the models can improve further as long as the other keeps the same strategy. And this would correspond to the Nash equilibrium in GAN theory. And at that point, again, ideally, the generator will have learned to create data that looks as if it was coming from the real data. I keep saying ideally because GANs can be a bit fussy, a bit more actually, and maybe quite difficult to train at times. But they are also very rewarding if the training is successful. Our research is motivated mainly by an observation of how GAN models and one-class classifiers relate to the real data subspace or the real data manifold. Namely, a one-class classifier will attempt to somehow place a border around this space, while a GAN will drive its output that starts out as random, will drive it towards inside the space. So it's not very far-fetched to imagine that this output of GANs will travel from random areas of the space progressively as training progresses, will travel towards the real data space. And at some point, they will be really close to it, but not inside there as well. And maybe at that point, we can use the samples generated by the GAN to formulate a binary classification problem of those samples versus the real data samples, and hence train our one-class classifier in a binary classification configuration. So our hypothesis is that the discriminators and the images generated during GAN training can be used to create a one-class classifier. Let us look now at the one-class classification problem from a slightly different perspective. Imagine an oversimplified case, such as this one, where our data is bidimensional and concentrated in a small region of the space and almost convex. Imagine also that we have a process that draws random lines through this space, with the sole condition that no line is allowed to pass through the data points, but otherwise completely random. If we leave this process to run indefinitely, eventually the lines will completely surround our data space. And if we call these lines borders and combine them actually into a single border, then we obtain a pretty good looking one-class classifier. This, of course, is not really possible in higher dimensions, where it would be simply intractable. But our idea is, what if we could force these random lines to be generated only in a close vicinity of the real data manifold, instead of being generated all over the place. Then we might be able to reduce drastically the time we need for all the borders to completely surround our data, and hence we would be able to create a one-class classifier in reasonable time. And on how we could achieve this, we turn again to GANs. And so we'll say that again, GANs were trained by moving their output from a random region towards the positive, towards the real data. And you can actually see in this video how a GAN trains. Red dots are the synthetic generated samples, green dots are the real samples. And they do that by the use of a discriminator, a classifier, that permanently tries to put itself between the synthetic and the real data. So our idea is that, one, we could use the output of a GAN, a synthetic data samples, while they do not overlap the positive data yet, to create borders by creating a binary classification problem between those samples and the real samples. Moreover, since we already have this discriminator that attempts to do just that, place itself in between, we could attempt to directly use the discriminator for this. And lastly, we would like to delay, if not inhibit completely, the overlap, the moment when the generated data penetrates the real data space. And this finally leads us to our algorithm, which does just that. So essentially, we take a GAN model and we train it using the standard procedures, but with a very slight modification of the loss function that encourages the discriminator to always to classify the positive data, the real data, correctly, while the same condition is not necessarily imposed on the synthetic data. After each training epoch, after we update the discriminator, we make a copy of it, we save it. At the same time, we have our one-class classification model that starts out as empty, but as we collect the discriminators, we append them to our one-class classifier. And our model will essentially multiply the output of each of these mini classifiers, of each of the discriminators collected during the GAN training. And this is our model, our algorithm. Turning now to experiments, to test it, we used two data sets, MNIST, containing, it's a data set of 10 classes, containing handwritten images of the 10 digits, 0 to 9. And Cipher10, again, an image data set of 10 classes, this time containing real-world pictures of certain objects, such as trucks or planes or cars. As a training strategy, we take each class in turn from each data set and consider it the positive data, while the other classes will form the negative data. So we create a training data set with samples from our positive data, and then we create a test data set balanced with samples from our positive data and random samples from our negative data from the other classes. As a measure of performance, we use the area under the, before that, using our training data set, we train our one-class classification model. Then for testing and to measure performance, we use the area under the ROC curve obtained for the classification of the test data set. And finally, we also measure the mean AUC obtained across all the classes. Turning to results, what you see here are results of experiments on the MNIST dataset. We have a table with 11 rows corresponding to 11 methods, last one, GAN OCC, being our method, while the columns correspond to the 10 classes of MNIST, digits 0 to 9, with the last column being the mean AUC. And of course, the values in the cells are AUCs obtained by various models. Our model achieves the highest mean AUC overall, albeit with a pretty small margin, but results AUCs on this dataset are pretty high. It's not a very complex dataset. And we also obtained the best class AUC on 5 out of 10 classes. Moving on to Cypher, this is a much more challenging dataset, and this is reflected in the AUCs you see across the board here. Nevertheless, our model obtains again the best mean AUC, this time by a larger margin of 13%, and the best AUC on 6 out of 10 classes. There is plenty to discuss about this. I will be brief. I guess the most important thing is the observation of how the model behaves in reality versus how we would have expected and liked it to behave. So it's a very good thing that we obtain this benchmark results. It sort of validates that we are on the right path, that the idea is correct. But on the other hand, what we notice makes us realize that there's still a lot of work to do. For instance, what we would like is to see a continuous improvement in the AUC as the training of our model progresses, and as the GAN, the generator, moves its generated samples into various regions of the space, and borders get created as a consequence in those regions. However, what we notice is that most of the improvement takes place during the early stages, while in the later stages we either see really small improvements, or we can even see the system degrading slowly. And we attribute this to the GAN model acting as a resource that eventually gets exhausted, and the generated samples either start penetrating the real data space, and at that moment we can no longer produce useful borders, or they go into mode collapse. This is a particular regime of GANs where they basically create the same image, the same output, no matter what the input is. So we don't have enough variation. And overall, this better control of the GANs and being able to move their output into a more varied area of space that is still nearby the real data space, this seems to be the key to improving the algorithm further. As part of our future plans, of course, developing the algorithm further is very important, if not essential, but we also plan to use it in practice, and in particular, I apologize, not exactly sure why this happened, and in particular for predicting the risk of dementia. This is a very a very serious problem within the UK, and not only dementia takes a huge toll, not only financially, but also in terms of quality of life every year. If I'm not mistaken, it's higher than cancer and heart conditions combined. And we believe that we can predict the risk of dementia and therefore prevent, take action for many cases in time, and therefore increase the quality of life of the patients and reduce the costs. And this is a project in collaboration with the University of Manchester and led by Professor David Reeves. And led by Dr. Daniel Stamate on Goldsmiths, University of London. To say a few words about this future research, which is most interesting to us, we will be using CPRD, or clinical practice research data link data, healthcare data, containing records about roughly 13 million, roughly 1 million patients and 13 million records in total from 400 GP practices. Highly dimensional, almost 600 variables, which makes 13 million records not seem so much. And the target will be to predict dementia within the next 5 or 10 years. We plan to use deep learning techniques to test deep learning techniques on this problem, and in particular this GAN OCC algorithm, and why not other one-class classification methods, mainly because classifying the dementia can be seen as a particular case of one-class classification / anomaly detection, or classification with highly imbalanced data. Also, we have a large number of records and a large number of features, which makes the use case quite suitable for deep learning. Okay. As a conclusion, we presented here a novel method based on generative adversarial networks, more precisely on collecting and assembling discriminators as produced by generative adversarial networks during training, in order to create a one-class classification model. And we have proven that it can outperform other deep learning methods on the benchmark datasets. Thank you very much for your attention, and happy to answer any questions I know the answer to. Thank you.
Thanks very much, Mihai, for the excellent talk. I'm really looking forward to see the application of your work to the dementia data set. I think there are many challenges, but there can have very many benefits as well. So I'm going to open the turn of questions. So does anyone have a question for Mihai? You can just raise your hand and open your mic, or you can just write the question on the chat. Okay. Let's see. So Samara, please.
Thank you very much for this good presentation. It makes I had some difficulties understanding the paper, but now it's much better. As I understood that the core idea of GAN is based on indirect training through discriminator, which updates itself dynamically and regularly until it minimizes the distance or the differences to the real data and or the real image. My concern is how you overcome the issue of overfitting or the variance. So maybe the discriminator keeps updating itself. Is there any control or threshold on the model that you could develop? Thank you.
Yes. Yes, the discriminator permanently tries to put itself between the real data and the synthetic data. And the purpose of this is that eventually it will provide the gradients, it provides to the generator the necessary information that it needs in order to migrate its output towards the real data. And overfitting is avoided by not training the discriminator too much. So we during a GAN training, during an epoch, both the discriminator and the generator are trained for one step only. So the discriminator achieves a very weak classification between the real and the synthetic data. And this is exactly what we want and what we need, actually, because if it were a crisp classification, then the generator would have no information, no gradients to update. I hope this answers it a bit.
Yes, thank you. But how the discriminator knows that it has to stop on a certain threshold and stop updating itself?
Oh, it doesn't know by itself. We just specify that it will train for a single epoch with these hyperparameters.
So the developer, all right, okay.
Just takes one training step, no more.
Oh, thank you very much.
Thanks very much for the answer. So I think that Diana has raised her hand. I don't know if you still have a question, Diana. Okay, the question is now in the chat. It's fine. So Diana is saying, thank you for the presentation. I wonder if you also control for calibration quality of the model, not just AUC for discrimination. As with non-linear approaches, this is where often can suffer, even when discrimination is good.
We don't. We have, truth be told, pretty little control on the moment, and we don't have the right levers to tweak the way this border is created. This is part of our ongoing research and improving the algorithm.
Okay. There's another question by John Langham. The question is, how computationally efficient is the method?
It is, we have been using the vanilla deep convolutional GAN as a generator, and very simple neural network neurons as the discriminator. So it's the complexity of the algorithm is just the same as the complexity of training a GAN. And in terms of number of operations and complexity, it is slightly lower than training a normal GAN, the GAN training part, plus the added operations for composing the one class classifier.
So thanks for the answer. I hope, John, that this is answering your question. I do have another question as well. So you said that you will be working with primary care data records for your dementia analysis. So I was just thinking in the application of your method to real data and data that, so you said you have like more than 1 million people in the data set, and you have 600 measures. But you said that you will be predicting dementia risk at 5 or 10 years. So I understand correctly that this is longitudinal data. So you would have repeated measurements for the 600 variables. It's like that. Okay, so you will have probably missed the records and loss of information. So have you ever thought how you would deal with this, or how your method will deal with this?
Not yet, to be honest. This project is just, well, the project has been ongoing for a while, but I'm just joining it and cannot say I'm very familiar with the data. Daniel may be able to provide more details on this.
Yeah, I may intervene a little bit. Thank you for that, Mihai. So yeah, definitely the project has been on work for a while, and we currently develop different methods, starting with statistical methods. The team at Manchester is dealing with that. And also we at Goldsmiths, we develop machine learning methodologies. And definitely we have put in place some of the techniques to handle the longitudinal aspects of the data. And so currently, John Langham, who is with us today, so he develops such models with me at Goldsmiths. And also the teams at Manchester, they do the same with different models. So including models from the survival area till applying different techniques on pre-processing the data, such that we take advantage of the time longitudinal aspects in the data. So in particular, flattening data is one of the techniques. And so far we got pretty good results on this kind of approach. Hopefully another paper will be submitted shortly, and so John will probably be invited in this seminar to present this kind of developments. And Mihai, just to as he mentioned, he just joined the project, and then he's specialist in deep learning and neural networks. So definitely he will take advantage of the pre-processing we have done on this data, and he will bring into the work the advantage of applying these state-of-the-art techniques like deep learning. So definitely he will take advantage of the longitudinal aspects in this analysis.
Thanks very much, Daniel. I think that the other Daniel still is having a question as well. Daniel.
Yeah, thanks a lot for this really interesting presentation. I think this kind of method can be used a lot in psychiatry, because we might look at just at the population, want to identify people who develop schizophrenia. So I've got two questions. Like, one would be more, how well does it generalize to new situation, your model? If you've got your figures which you identified, you had like separated humans from horses, but if you have now pictures with cars, can it still identify the humans, for example? That would be my first question. The second would be, would it work with sparse data, like schizophrenia that's less than 1% of the population will develop it? Would you be able to develop a model for sparse data?
Yeah, thanks for the questions. Trying to answer the first one. Yes, that is an issue, definitely. So I will give one example from the data sets we've used from Cypher10. For instance, our algorithm is able to distinguish sheeps from frogs, for instance, much better than sheeps from airplanes, which kind of makes sense because if you think about it, ships and airplanes tend to appear with the same type of background, the bluish sky or sea. So this is indeed a challenge, and we've noticed that it is able to separate the classes, albeit not with the same accuracy. As to how it will behave, how does this translate on a real data set? I imagine the challenges will stand. Secondly, about your second question, I expect it will work quite well as long as the other challenges can be overcome, because in my opinion, this is exactly this is in the very nature of the algorithm. This is what it's supposed to do. It's supposed to handle classification when we have either a single class of objects at our disposal. So imagine we would have only persons without schizophrenia, or a massive class of positive data and a tiny, only a few examples of negative data. So I expect that as long as the algorithm can do what it's supposed to do, it should apply well on such use cases.
Okay, thank you.
Daniel, please.
The other Daniel.
Yes, the other Daniel.
Sorry, I think Mihai already answered what I want to ask, but maybe just to point out the fact that indeed, I think in one of the slides he had this information, but maybe he just passed to the next one. So definitely, it's not only the application of this algorithm for the new approach in predicting dementia. This would be useful as a one-class classification, so dementia versus all. But also other techniques related to deep learning as this one may be suitable for this modeling, because in particular GANs, which is one of the elements of this algorithm. So GANs can generate new data, and Mihai actually illustrated very nicely one of the images which was generated, which was very similar to real images. In other words, GANs can generate data which has distributions very similar to real data. So how this can be applied in this project? Definitely, as dementia cases are very few compared to the general population. Basically, this is a challenge for machine learning algorithms, as we know. So in general, we would need a kind of balancing, which Mihai mentioned. So GANs may be good to generate data which is similar to dementia cases. And this kind of data records can be put in the training aspect of the algorithm, not in the test, of course. For the test, we can use real data, but on the training side, so such that you can have a better balance of the data, which would alleviate the problem of data imbalance, which is a problem for the machine learning algorithms. So GANs can generate this kind of data with distributions that we want, which in terms of our application would be patients which are synthetic patients, but similar to dementia patients, which can actually help the algorithm to train better on the data, on the training set. And then, of course, we measure and we validate the model only on real data. So that's one of the applications of the GANs, which Mihai is doing. And another one would be using other techniques in deep learning. Like autoencoders, because another challenge is the high dimensionality of the data, and given that there is a lot of records in the data, so this may be a challenge. And John asked about the computational efficiency of the calculation. So from this point of view, we are looking to other methods to reduce dimensionality. And one of these deep learning techniques, like autoencoders, may be used to do that. So definitely, this can go together with the algorithm that Mihai proposed, and with the other deep learning cutting edge techniques in deep learning to use together in this challenging problem. So just to point out this, because I think Mihai wanted to do it, but I think also he wanted to fit in a given amount of time.
Mhm.
Thank you very much, Daniel. So I think there's no other questions now in the chat. Oh, there's a chat. Okay, yes, David, I think.
Hi,
David? Yes, please go.
Yeah, hi. Yeah, thanks very much, Mihai. That was really interesting, and I'm really looking forward to seeing how that performs with the CPRD data. I think that's going to be very exciting because it is extremely challenging data in terms of imbalance and in terms of censored cases as well. I had a couple of questions. One is that presumably, even with your one class classification, you have both false positives and false negatives. And do you have a way of sort of weighting for which of those you want to control for most with the model?
Thank you very much, Professor Reeves. Short answer is no, not yet.
Okay.
Yeah, we can impose some conditions on the discriminators during training, such that, for instance, we can ask them to always be strictly on the good side, keep the real data on the good side. In this case, we may be able to obtain something like a very high recall, for instance. But this approach also tends to have secondary and not so desirable effects in terms of overall performance. So it's something we're still trying to figure out what to do. And I guess the key is taking this algorithm one step further, one more step of improvement to it.
Right. Thank you. I also had a second question, which is that if you think about the multi-class problem, can that be expressed as it were a series of one-class classifications? So in other words, each of the multi-classes, you analyze each of those as a separate one-class classification?
Absolutely. It's and in my opinion, it provides many advantages taking this approach. The only caveat is that we need the one class classification model to achieve an acceptable level of performance. So depending on the situation, we might be able to do it practically, but I expect that in a good number of cases, a one class classifier will have a lower performance when separating A from B than a binary classifier trained specifically to separate A and B, if that makes sense.
Right, yeah. Thank you.
Thanks very much, Professor Reeves. Is there any other comment related with this? There is another hand raised, but I think that is because of your previous question, isn't it, Daniel?
Sorry, yeah. Yes.
It's okay.
Sorry.
I don't have a final comment. I was just thinking that if your final aim is implementation of your model for the dementia risk prediction, I was just thinking that when you probably know perfectly that when we use so complex models for a real practical clinical implementation application, there is a challenge that is finding this balance between accuracy and interpretability. So I was just wondering if you have ideas on how to inspect your feature importance or the interpretation of your models so that they can be understood by psychiatrists and people that are going to be using them, because it's this opacity of some kind of this kind of models sometimes is a barrier for them to be implemented in clinical practice. It's just a comment, something that you can anticipate. Probably it's too early, but I was just wondering if you had any rough idea on how to explore the feature importance of your model and the interpretability of it.
Yes, thank you. No, I think you are absolutely right, and I expect we will run into this. I can't say I thought too much about this for the use case we're dealing with for dementia. I can just talk from previous, from my past experience. I know we've been using SHAP to explain complex models. Well, up to a certain limit. You cannot go too far with it. But provide a hint of why a model took a certain decision or provided a certain output. This method used to work pretty well, as far as I can remember. So it's just an option, not saying that this is the.
No, that's very interesting. Yep, thank you. Again, there are two hands raised. Is someone that want to talk again, or are just left there?
They're left.
Sorry.
I don't know how to get rid of it. I've no idea how to get the hand off.
No worries, no worries.
I've tried pressing other symbols, but it doesn't work.
It's okay. Okay, well, I think that actually we are already at 5 o'clock. So if there's no other question, I think there's not. So we will give the seminar for finish today. So many thanks, Mihai, for your talk. Excellent presentation. At least I enjoyed it a lot, and I think that the rest of the audience did as well because of your questions and the discussion that you generated. So thanks very much for all the attendance. You are invited to join these meetings every month here at King's. And just telling you that so this has been recorded. So if you want to go through the talk and so to see the slides again or to listen the explanations from Mihai, you can do it from the NIHR Maudsley VRC Prediction Modeling Group webpage. And what else? The next week next month we will be on holidays and we will be back in September again. So I don't think I'm missing anything. Daniel, Stoll, would you like to add anything else? If not, we will finish the talk here. Okay, so that.